Hello, welcome back on Heterocyclic Chemistry. So we'll be continuing presenting the work on heterocyclic chemistry, and last time we have been talking about the three-member ring: aziridine, thiophene, and epoxide. We talk about the biochemistry of the three-member ring, the biochemistry of the three-member rings. Okay, so today we expand the study on cycle bigger than 3. Okay, so just finish first. We will be finishing first the work on the 3-member ring, then continue on the 6-member ring and 5-member ring cycles. Just give me 1 second, I just need to connect. Okay. So as I said, all these courses are oriented for research, for your studies and for your research. So it's for research. Small back. It's for research, and during each courses you will have at least 2 to 5 new projects. Okay, so we first study the topic and we explore a step on the side, not in depth, a step in the side, what we can do. Okay, step on the side. Okay, I have a small bug. I need to delete. Unfortunately, I need to delete. Doesn't want to move. I do it like this. Okay. So last time we present the work on testosterone, the advantage of using epoxide in for biochemical processes. Sorry, today I have. Okay, now it's fine. So you have different natural product. The presence of epoxide in natural products is found in antibiotics, in some toxin. I'll give you some example. One example. In fatty acid, yes, and so on. Okay, so some example of epoxide found in toxin. Just a nice example. H, this one up. A nice compound. So I will teach you how to make this compound. Teach you how. Teach you, sorry. Teach you how to make it. We need to study the book of Eric Carrera because you need to know. So it's quite easy compound. You just deal solder on some cyclization and site specific epoxidation. Eric Carrera. Book. And Andrew Myers. Yeah, why not? We can present on this channel the book of Phil Barron. Okay. If you understand where we can like study how these three professors work individually, then I'll teach you how to make it. So you remember last time I told you if you have one alcohol nearby an epoxide, this product is quite unstable at pH 10, 11. Yeah, because you generate a little at pH over 11. You can get some intramolecular, even if here it's on the top, but you can maybe have some polymerization. If intramolecular is not easy, I was looking for the pen reaction, but this way. But you can get also some beta elimination. Yeah, beta elimination. It's very unstable under basic condition. I was thinking about the domino cyclization. We talk about this Naka Nishi cyclization. To form polyether. Well, I'll redraw it again. Soon we don't need to do, maybe I will help you if you follow my channel and subscribe. We have been making a powerful tool for all types of science in one shot, a real brain. If you follow me, I will provide you one license. It's the first one. It doesn't still exist, but we are doing a lot of things until it's become perfect. Okay, double bond. Oh, sorry. I know this pencil is not easy to delete normally. When it's full screen, you cannot delete. Well, anyway, it's down. Okay, watch. I am Mirchin. Is there anyone who made this? Not, I think it's not. The most complex part is for me. Even, it's not. It's to control this stereochemistry of this tertiary carbon. I would do a lot of study but the rest is easy, It's not so hard to introduce this epoxide with ester. You can make like an iodo-lactonization. And this one you can add it on ketone addition. Then you can do an epoxidation. Yeah, IQ. Bam, you can get your compound. But it's not so easy to work with tertiary carbon. Okay, another alcohol that is interesting. Oh, this hormone is named Sphinx. I like it. Sphinx hormone. Nice. It's from Night Butterfly. So this compound. Sphinx hormone. I don't know why it's called like this, but it doesn't look like so impressive, but maybe it has some special effect. I I've never heard about this compound, but well, okay. O2H. Okay, this is a thing, and you have this epoxide, and it's found in plants. Oh my god! I told you I'm sorry for the drawing because my hand was broken, so I have some. Broke my hand like 7 years ago, and I stopped. Even more. 9 years ago. No matter. 3.5. Biochemistry of siren. You know, it's something interesting. It's not well known. By that time, huh? This book was published in by 2007. Biochemistry of siren. Nothing. So because there's no natural product containing this cycle. Why nature doesn't use this one? Maybe because of the sulfide is too much, but maybe it's too much reactive. Maybe because of the reactivity. Too much reactive. Why this one in a cell you find it in natural products, and this one nothing? That's a good question. Maybe it's too much reactive, and nature doesn't want something too not so easy to control. Maybe it polymerize, so you have polymerization, and it could like precipitate the cell and kill it. You know what? It's interesting. If nature doesn't want it, you can use it. Use it. Special cascade alkylation force. You can use it as a DNA drug. Yeah, maybe I would do something like this to cut DNA. I had can add a thymine. I'm just saying randomly. I'm not saying it will work. Okay. Can use it as a backbone for guanidinium. Namide. If it hybridizes here, you can think about an amine, strong amine like guanine. Here, then it can sulfide can, for example, I'm not saying that it works, no? Just a proposal. If you have a DNA base 1, base 2, so if you make, I don't know, base 2, for example, with 2, 4, like you can have your here, your cysteine, sorry, like cysteine, like we don't care. If there's an NH2 DNA base, a base with NH2 can open, or here, or here. It attack here, obviously. We talked last time about the Donist angle, okay? So you open the least substituted. That means you get like okay. Then I'm not saying it's working. There's protonation. What I like in sulfide, it can cut DNA. Could cut DNA. All right. Nice. I have many projects like small compound. Well, if you want to work with us, you can let us know. And it's really new, completely new concept, even new concept for sequencing. Using small compound and orthogonal chemistry. And imagine you have a phosphate backbone. Okay, DNF, the SH could cut it. Could cut. Okay, let's make a sizer. Oh my god. Let's retry. Let's make a decent sizer. Not laugh at me. I'm trying. Okay, a sizer. All right. Okay, so it cut. Okay. I'm just checking if everything is fine with the live. That's interesting. I'm very interested. When there's nothing, no, not many. Maybe I should check. Huh? If it's true, that's very interesting to use this motif in biology. It could be interesting. to use it. Yeah. It could be interesting. Yeah. To use it. Sound is perfect. So now continue on aziridine. We continue. 3-6. What is it? 3-6. Biochemistry. Of always when you have something, explore it. Okay. This step on the side. So sometimes you can find two things together and you merge them. That's if you find a node here, a new node, you can create a new node. Most of the scientists, they use this method. That could be Grubbs. He got Nobel laureate with this strategy of creativity. I'm making some courses about on my channel, my other channel, Research Edutica. I give some courses about creativity. I have been giving some courses. I started with Einstein, but I will continue with most of the more. But this strategy, not many people, I mean, not many people are successful. Like you create new nodes and edges. You need a lot of trials to make quite poor, fast results. Poorly famous. I don't like the word famous at all. You have less chance to be famous by this method. But some of people grabs, not only grabs, who use this strategy. Ojatsin. Oh god. Len. Maybe the most two famous, but the rest are. But you cannot be pioneer. That means it's super hard to be the first, the first with this method. But keep it in mind. I call it step on the side. Just connecting some nodes. Okay. Nice. So aziridine. About the biological application of the aziridine. Okay. What can we say? So aziridine are very interesting DNA. We talk about DNA, but I don't know why. Maybe they are more stable. DNA. That's the reason why nature doesn't use too much thiophene. Aziridine. So free membering are great DNA alkylating reagents. Okay, and typically one professor who uses them a lot to do what I showed you, it's Professor Peter Dervan. He is the former supervisor of, if I don't know, Peter Schultz. Carrère, if I remember. I don't know if it's PhD or Carrère, Eric Carrère, and many other. So one of a compound that is broadly used, but I mean at least in the past, mitomycin, a very nice compound that I like very much. Symbol mitomycin. So it's the same as what I showed you with the example with thiophene, the thiophene that I showed you. Okay, it's similar mechanism. Okay, let's finish the biochemistry of the free membering on. Again, it's the older. This book is before 2005. Later, because I want to cover before 2005, and a book that covers to 2015. Okay, but if you check what people are publishing now, there is absolutely no revolution. It's just using more. They use more metals, but a few people use traditional chemistry. So you don't. If you study until 2005, it's enough to start to have a fit on scientific projects, if you can do it. Let's start. Okay, mitomycin, this is a compound. I have tons of projects like this on methodology, like Dervan project like this. Again, but I'm not fan of, because it would have interested me like 30 years ago, but not now. I mean, I could do it just for. But doesn't excite me at all. I have no interest. Despite this could be interesting, very interesting. Okay, this is mitomycin. This is an antibiotic. I guess an anti-cancer. Anti-cancer. Why? How you can recognize that it's an anti-cancer? It's quite simple. All compound with a flat. Okay, I had N. Okay, N. No matter. no matter the number of rings. If it's flat aromatic, and DNA, they are called DNA intercalating. If there is no bulky, not too much, no, if there is if there is no huge bulky group, otherwise it works, it always works. Flat aromatic, it's a DNA alkyl. But if it's crescent, it's specific to the double helix. Okay, if it's crescent, because the DNA is like, you know, it's double helical. Okay, so you have minor groove and major groove, minor groove, and major groove. So it goes mainly inside the minor groove, and the DNA, you see, it has a curvature, okay, like this. So if it's crescent, it's more specific to DNA, because RNA is most of the time single-stranded. Double-stranded are not so not many examples. I mean, less examples, sorry. So you have more chance to interact with DNA. So I come back to the mitomycin. The mechanism is similar, okay? It's something that it's funny to present. So what you have, so if you analyze, always analyze your molecule. Okay. So you see here, you can see by from visibly, it's very hindered, like very restricted, high torsion. So it's not very stable because it's very ring torsion, too much ring torsion. So it wants to remove some compounds, and I see it immediately here. This one, and this one, and I don't know about this compound. And here you can see it's flat aromatic, so it goes to the DNA minor groove DNA. Okay, so I see that this motif is very unstable. This one is not comfortable, and this one is very the torsion is very high. So I think there's a mechanism involving these three. So there's a group living here, there's a group living here, and there is no most probably azerian opening. What do they say in the book? Yeah, it's right. Yeah. So I try to represent you the compound in the space. So if you look at this diode, this one will go down, so we go behind, yeah, like this. Yeah, so you see, then you have this one that go below, come back, come back like this, like this. And this one, this. You see, it's too much torsion. Okay, you see that this one is not comfortable, this one is not comfortable, and this one is not comfortable. There are some clashes here. Yeah, a lot of clashes. It's not an easy compound to make. Not so easy because it's very unstable. Like, don't never use a base. You should never use a base on this compound. Okay. So the mechanism. So I go back to the slide. This type of chemistry was famous in the past. Nowadays, not too much. Because there's a lot of drug resistance with mitomycin. And it's quite toxic compound because it can target any type of DNA, including the normal the DNA of a normal cell, so it has a certain cytotoxicity. I don't think that's something that people employ nowadays. Just for pleasure, okay? We do it just for pleasure. Okay, no matter here. First step, it oxidizes. It reduces. First step is a reduction. Why and how? Maybe oxygen is enough inside DNA. this word is exploring and do what you have to do. Terrible and beautiful. So you have to focus on the why. I'm sure it's involved in NDPH. Yeah, but it's not precise in the book. Who cares? We care. Is it possible to use it to destroy the spike? COVID spike? I don't think so, because it has a lot of cytotoxicity. It's very cytotoxic. Cytotoxic. Toxic. Then life is beautiful when you explore like this. So I told you the methyl is not very comfortable. Huh? When you represent it, always represent even a scheme like this, you see that there's a lot of clash and it wants to go as soon as possible. So you have elimination of methanol, and also methanol is not safe. Huh? It's toxic. So that's why this compound nobody. I will check tomorrow if it's still used, but I think we are much better compound than you. For each compound you have 1 mole of methanol. No way. Maybe they should tune it with ethanol, but even ethanol release some alcohol. Well, in all cells, I don't think it's so safe. And okay, double bond here. All right. You know, hindrance compound like this, and torsion, with a lot of torsion, are very interesting, because you can activate them, activable. They have low stability, so you can form, you can have low stability and form easily a new compound, more stable. So had some tension, sorry, it's not torsion, tension, there's a lot of tension and torsion obviously, but a lot of tension, compound with a lot of tension with ring tension, ring, to strike a targeted compound. For example, I'll give you one example. You have your methanol. Instead of methanol, you use like nemolative system. So can kick out. Yeah, to make it activable. On off. Activation, I should say on demand. Well, no matter. So we were here. I draw back the H2. If you study like this all the steps, or if you study each ring like this on the side, like as I'm doing exploring left side, so you do the same for each type of rings. Like if you have a compound with 5, 6, 7, so you know that 5 I can do like this. I can find some common nodes with 6. I can find some common nodes with 3. So you can find a pathway like this. That's why step on the side and total synthesis is very interesting. Study. I'm talking about the study. Huh? So I come back to my ring. I finish automycin. Then I guarantee you can be able, if you do my method, you are able to make any type of compound. Normally you are. Okay, so now what's next? So you get this compound, you kick out your methanol. I guess there is something that attack here, or I think 1 point interaction. Yes, I was right. It is that. So here now the DNA. You need two DNA base. In fact, what would happen? One DNA base will help to attack at this position, and another one attack at this position. Yeah. So the product is so today we will have been accomplished 20% of the book, okay, in total by the end of the day. So if you follow me, you will know everything about chemistry. And how to innovate chemistry humbly. So I like this mechanism, this type of mechanism. So now you need to activate this double bond. This double bond should go here. This one here, this one here, this one here. Okay. So 1, 2, 3, 4, The aim is to eliminate this group. Then the DNA can attack on the double bond. You know, when I talk about creativity, it can be molecular machine, it could be any reticulated chemistry, so you can use this type of reaction. I guarantee you make like a MOF, you use this type of reaction to release your compound, or you send it to Nature Chemistry, they accept it, if you have a real student working with you. It's even a very good project. Like on demand release. I mean, not very, I mean, interesting. I don't like. Yeah, I see. Maybe I should isomerize first. Yeah, what I advise you, when you do something like this, try to find yourself the mechanism, okay, and explore some on one or two example. Find yourself and try on 2 or 3 example. You can even create this example yourself, so it will increase your memory. So what could happen? Oh no, sorry. Oh, let me redraw it if I remember. Is CH3. The best way to practice is to do it by yourself, and don't hesitate to make mistakes, as I'm doing. Like this, next time you know everything in detail. So I isomerize. So now I put the double bond here. I didn't use the right result. I understand. I should. Kick out first this one. Yeah. So first I open the ring. So I have the plus here. There's a minus. I'm just checking if I move. Put double bond here. Then how can I do? Yeah. Can this one remove? Take this one. This one come here. This one come here. Yeah, I like it. Then you get, because you know, remember, acid or basic reaction, basic acido. Then this one, pick up this one, then you have reform. Tac. You see here this motif, double bond. You can add a name in here. This one cannot attack back because it's hindered. You know, you come back. Okay, so I guess there's a DNA coming here. This one come back. Okay, you form the OH. Then the OH come back and kick out this one. Yes, and when kick out, you make a double bond. There's okay, like this. So first you have a DNA attack from here. This double bond. Okay, so you have the 1,6 addition. Tac, tac, and tac. Then he takes the H of the second H. Okay, so you have this product. All right. So you have the NH. I think come from the app because remember there's this one down. It should be on the upper side. DNA. This double bond. Okay. Yes, this is that. Then this one is this one. Kick out this motif. So you get I don't want to do course like everything they just take the book and read the book. Here we do everything ourselves. I don't read the book, I just look at it briefly and do it. And I can, anytime I can reproduce it anywhere. Okay, so here you have a double bond, so it's not from this side because here it's many from here. DNA 1, NH2, DNA 2. DNA 1. Okay, so this is a one micromycin is very strong. It alkylation of 2 DNA base. Okay, so let's have a small rest of, and we come back in 1-2 hours. See you and keep going.